Let's discuss about the BJT configuration. In BJT, as we know that BJT has three terminals: emitter terminal, the second is the collector terminal, and third one is the base terminal. So in BJT, we know that there is a one input node, there is a one output node, and one is a common node. At input terminal, let's assume there is a current that is flowed at input terminal is I1, and the current that flow through the output terminal is called I2, and there is a voltage at the input terminal is called V1 and output terminal is V2. Let's say this is the first node, this is the second node, and this is the third node. The third node or third terminal is common to input and output node. That's why it is called a common node. Now, BJT can be used in three configurations. The first one is common base configuration. In common base configuration, emitter is used as an input node and collector is taken as the output node. In second configuration, that is called the common emitter. In common emitter configuration, at input node, the base is used as an input node and collector is used at the output node. And in common collector configuration, base is at the input node and emitter is at the output node. Let's discuss about the common base configuration. This is a common base configuration for NPN transistor. In common base configuration, the base terminal, this is the base terminal of the transistor is common to emitter and collector, that is the output or input terminals. As we can see, the base terminal is common to emitter and collector. Let's discuss about the input characteristics of common base configuration. Input characteristics of a common base configuration is a plot of input current IE versus plot of input current IE versus VEB, while maintaining the output voltage VCB constant. Now, the input characteristics of common base configuration is look like the VI characteristics of diode. As we know that for NPN transistor, the emitter junction is forward biased and collector junction is reverse biased when transistor is active mode. So this junction, the PN, the emitter junction is like this, and if it is forward biased, so in case of VI characteristic of diode forward biased, the VI characteristic is like this. So it is input characteristics look like a VI characteristics of diode. Now let's say for example this curve is at VCB 1 at constant VCB, and let's say VCB 1. If we increase the value of VCB, let's say the VCB 2 is greater than VCB 1, then graph will look like this. If we further increase the value of VCB, then the graph will shift like this. So for a given value of VEB, higher emitter current will be obtained. For a given value of VEB, higher emitter current will be obtained for higher value of VCB. For higher value of VCB, as VCB 3 is greater than VCB 2 and greater than VCB 1. So as VCB increases, the input characteristics, that is the input characteristics, shift towards left. As we can see from the graph, the input characteristics shift towards left. Now let's discuss the output characteristics of VCB. The output characteristics of VCB is basically a plot of output current IC versus output voltage VCB while maintaining the input current. It is a plot between IC versus VCB while maintaining input current IE constant. So the input characteristics for the BJT, IC represent the current through the collector junction, VCB the voltage of collector junction. Now the net current through a collector junction, as we know, the net current through a collector junction is basically a superposition of two current or two component. The first one is the current which flows due to carriers of emitter reaching the collector region, that is the IPC, and the second is a current which flows due to carriers of base and collector when voltage is VCB. So it is basically a superposition of two currents. So if both junction are, this is the emitter junction and this is the collector junction. Now consider a case if both junction are in reverse bias, then these two current become negligible. These two currents become negligible. The current 1 and current 2 will be negligible, and therefore the current IC will be 0. And the region of graph, as we know, the IC is equal to alpha IE plus ICBO. So the region of the graph where IC is almost equal to 0 and IE is equal to 0 is called cutoff region. This region is called the cutoff region. Now when both junction are operated in forward bias, the junction, emitter junction and collector junction both are operated in forward bias, the net current, the two current will be in forward current, and as VCB is gradually and the output value for a given value of IE will be this, let's say 2 milliampere. If you further increase the value of IE, you get a value like this. Let's say for example 3 ampere. For further value of IE, we will get a value like this. And here the I1, I2, I3, and the I3 is greater than I2 and is greater than I1. The region, this region of graph is called the active region, and this region of graph is called a saturation region. The region of graph where IC increases with VCB, as VCB increases, IC increases, then the region is called the saturation region. And the region of the graph where IC become almost constant is called the active region. IC become almost constant with VCB is called the active region.